Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the transient heat conduction in semi-infinite solid. Semi-infinite solid. We know that in the previous lecture we have discussed about the transient heat conduction, the lump system. In this lecture we will discuss about the transient heat conduction in the semi-infinite solid. First of all, you should know that there is a difference between the steady state heat conduction and the unsteady state heat conduction. In the steady state heat conduction, the temperature was not changes with time. The accumulation term was 0 in the steady state heat conduction. Now in the unsteady state heat conduction, the temperature can be changes with time. It can be changes. Temperature changes with the passage of time. It can be increase or decrease with the passage of time. This is the temperature. It can increase, decreases, or it can be increases with the passage of time. The temperature also changes with x direction or y direction or z direction. It can be increases or decreases. We have also discussed the lump system and Bévet number. We discussed Bévet number and we said that for lump system, for complete lump system, the Bévet number is 0 because the temperature was constant at every point in the lump system. So the Bévet number, we also discussed the criteria for Bévet for lump system, that Bévet number should be equal or less than 0.1. So in this lecture we will discuss the transient heat conduction. We also discuss the heat transfer equation in the Cartesian coordinate system, the cylindrical coordinate system, and in the spherical coordinate system. We know the general heat conduction equation in the three-dimensional Cartesian coordinate system is partial square t, partial x square, partial square t, partial y square, partial square t, partial z square, plus energy generation rate, thermal conductivity of the material, 1 over thermal diffusivity, change in temperature with the passage of time. So for the three-dimensional Cartesian coordinate system, the general energy balance equation is this. So this is called the Fourier. This equation is called the Fourier Bévet equation. Now if the energy generation term is 0 and if the accumulation term becomes 0, then this equation will become Laplace equation, and it can be written as partial square t, partial square x square, partial square t, partial y square, partial square t, partial z square is equal to 0. This equation is called Laplace equation. Laplace equation. There is another equation which is called the heat diffusion equation, which is partial square t, partial x square, partial square t, partial y square, partial square t, partial z square is equal to 1 over thermal diffusivity, change in temperature with change in time. This equation is called diffusion equation. Heat diffusion equation. Heat diffusion equation. Now this equation is called the diffusion equation. There is another equation which is partial x square, partial square t, partial y square, partial square t, partial z square, plus energy generation thermal conductivity is equal to 0. This equation is called Poisson equation. Poisson equation. So there are various equations for Cartesian coordinate system. So we will discuss in this lecture, we will discuss the heat diffusion equation only in one direction. Mean the temperature in the y direction will be constant. So this term will be 0. The temperature in z direction will be constant, so this term will be 0 and this term will be also 0. We will discuss the heat transfer only in the x direction in the semi-infinite solid. The meaning of this equation is that the temperature coming in the x direction, temperature changes, or temperature coming in the y direction, or the heat coming in the x direction, the heat coming in the y direction, and the heat coming in the z direction to a point or to a region is equal to increase in the temperature of the region. So the heat coming to a region in the Cartesian coordinate system, and as a result the temperature of the region increases. So energy N is equal to energy accumulated. So this is the energy equation and it is called heat diffusion equation. So in this case we will discuss the heat diffusion equation only in the x direction. The temperature will only changes in the x direction in the semi-infinite solid, and these two terms will be 0 because the temperature will constant in the y and z direction. So this derivative and this derivative will be 0. So now let's see. So the simplified energy balance equation is, which is the heat diffusion equation, partial square T partial x square is equal to 1 over thermal diffusivity, change in temperature and change in time. This equation is this is the heat diffusion equation in one direction, only in the x direction. Now first of all we should know that what is semi-infinite solid. A semi-infinite solid, like this is the semi-infinite solid, suppose this is semi-infinite solid. A semi-infinite solid body has one plane surface. This is the plane surface, this one. This is the plane surface. A semi-infinite solid has one plane surface. Plane surface, and it extend to infinity in all directions. Suppose this is the x direction, so it extends to infinity in the x direction, extends to infinity. This is the y direction, it extends to infinity in the y direction. This is the y direction, this is the x direction. So and this is the z direction, this is the z direction. So this is the z direction minus z or minus infinity. So this is the x, y and z direction. So a semi-infinite solid body has one plane surface. This is the plane surface, this one, the plane surface, and it extends to infinity in all directions. Remember, in this case the heat transfer only in the x direction. The temperature will change only in this x direction. The temperature is constant in this y direction and in z direction. So the two terms all are cancelled in the heat diffusion equation, and we get this simplified term, which is the heat diffusion equation only in the x direction. So the temperature in the x direction will be decreases the passage of with the x direction and also with the passage of time. Suppose this is at time is equal to 1 hour, at 2 hours the temperature is this, at 3 hours the temperature in the body is this, and it also decreases with x direction, So the temperature changes with x direction, and it also changes with the time. Suppose this is the time t1, t2 and time t3. So with the passage of time, the temperature increases in the body, and with x direction the temperature decreases in the semi-infinite solid object. So this is the semi-infinite solid. The best example of semi-infinite solid is Earth. Earth is an example of semi-infinite solid. If we are interested to measure the temperature near the surface of the Earth, then it can act as semi-infinite solid object. Similarly, a long plane wall can also be considered as semi-infinite solid. So the Earth can be considered as semi-infinite solid. Sometimes in analysis we use the Earth is semi-infinite solid. So there are various examples of semi-infinite solid. So how we will now we will derive equation for the semi-infinite solid object, and we will show that how the temperature decreases with the x direction in the body and with the passage of time in this semi-infinite solid. So we will derive equation, we will also draw graphical forms, and we will discuss other relation related to the semi-infinite solid object. So but remember, in this case the temperature changes only in the x direction, as you see from this equation. So let's see that how can we derive the equation for the semi-infinite solid. So the general energy equation was partial square T partial x square is equal to 1 over thermal diffusivity, change in temperature, change in time. Now this equation shows us that temperature is a function of x and time. Temperature is a function of time and x direction. So it is difficult to solve this equation by ordinary method. So we will use another approach to solve this equation to get a relation between temperature, time and x direction. So this equation cannot be, this is the second order partial differential equation. So this equation cannot be solved by separable or variable method. It is not easy to solve by separable or variable method. So we will derive some differential equation which can be easily solved by the method of separable or variable method. So now we will use some relation and we will get some ordinary differential equation, and then the ordinary differential we will solve the ordinary differential equation to get the relation between temperature, x and time. So now let's see, suppose this is equation number 1. Now we will use some dimensionless analysis to solve this second order partial differential equation, because the dimensionless analysis help us to solve our problem in less time, and it is the dimensionless number is very important in heat and mass transfer analysis, like the Nusselt number, the Reynolds number, which are very important number. So the dimension is, in the dimensionless analysis we combine various variable into a single variable, which can easily be derived and which is very helpful in various analysis. So these dimensionless analysis are very important in fluid mechanics, heat and mass transfer analysis. So in this example we will also use dimensionless analysis, which will help us to solve this second order partial differential equation. So let's see, we will use a dimensionless number which is called the similarity variable, and it is denoted by eta, which is equal to x divided by 4 alpha time. This is dimensionless number. The length, if you check its unit, then it is length meter, x direction is suppose length, and the unit of length square, and this is the time, this is also time cancel with time, cancel with this. It is a dimensionless number. It is dimensionless number. So we will use this dimensionless number And the importance of this dimensionless number is that this dimensionless number, similarity variable, this is the similarity variable. This similarity variable combine both x and time, and we are interested in x and time. So we will use this number. Now, how we will solve this equation? First of all, suppose this is equation number 2. The similarity variable is equation number 2. Now, take the right hand side of this equation. Take the right hand side, which is change in temperature with change in time. So, let's see change in temperature with change in time, which can also be written as change in temperature with change in similarity variable. Change in similarity variable with change in time. So this is a chain rule. By chain rule we can solve dt by dt, which is the right hand side of equation 1. So let's see how can we solve this further. Now dt by dt is equal to dt by d similarity variable and to similarity variable change in time. But we know that similarity variable is nothing but it is x divided by 4 alpha time under the root. So let's see that similarity variable changes with time. So this can be solved by derivative. So take the derivative of similarity variable with time. We will get time x divided by 4 alpha time under the root. So let's see, this can be solved by chain rule, as you know from your calculus, chain rule. So this can be solved by chain rule, and it is nothing but change in similarity variable with change in time is equal to, this is the second function, into derivative of first function, this is first function, minus first function, and to derivative of derivative of second, which is 4 alpha time 1 over 2 divided by second whole square. Now this cancel with this, and the x is not changes with time. The x direction in the semi-infinite solid object, the x is not changes with time. So this term is also 0. So let's further simplify this relation. Which is change in similarity variable with change in time is equal to minus x change in time 4 alpha time 1 over 2 4 alpha time. This is minus x, again this is by power rule, 1 over 2 4 alpha time 1 over 2, take the derivative again 4 alpha t, nothing but 4 alpha, this is 4 alpha time, 4 alpha cancel with 4 alpha, this cancel with this, and the answer is minus x divided by 2 is this 2 4 alpha time under the root into time, this time. So this number is dn by dt, but you know that the right hand side was dt by dt, which is nothing but dt by dn into dn by dt. So dn by dt is this number. So multiply this dn by dt with dt by dn, we will get dt by dt, this number. So simply multiply by this number by dt by dn, we will get similarly dt by dn, multiply. So we will get dt by dt. So this is the right hand side of equation 1. So let's see. So dt by dt is equal to minus x by 2t for alpha time. This alpha is the thermal diffusivity, and dt by dn. Now this is the right hand side of equation 1. Now suppose this is equation number 3. Now look at equation number 1, which was d square t dx square 1 over alpha dt by dt. So this dt by dt is equal to this whole number. So in place of this dt by dt, we will put this number in place of this dt by dt. Similarly, this is the right hand side, and then we will multiply by 1 over thermal diffusivity. So we will get the right hand side of equation 1. This is equation number 1. This equation is equation 1. Now we obtained the right hand side. Now we will will solve the left hand side. So the left hand side is partial by partial x, partial t by partial x. So this number can also be written as partial t by partial x. Now this partial t by partial x. So we can also write this as partial by partial n, partial t by partial x, partial n by partial x. Again this cancel with this, we can partial by partial x dt by dx. So this is again chain rule. Again chain rule. So partial n by partial x. So the left hand side of equation 1 is partial by partial x, t by partial x, which is nothing by partial n, so t by partial x, partial n by partial x. So we can solve this number because we know similarity variable x for alpha time. So change in partial with change in x is nothing but 1 over 4 alpha time. Calculus, from your calculus you know that the derivative of this number is this. So in place of this dn by dx, we will put 1 divided by 4 alpha time under the root. So let's put it partial by partial n, change in temperature with change in the x direction is equal to 1 over 4 alpha time under the root, which is the partial square t partial x square, or this number, or this. So again this is the now the change in temperature with change in x direction. This is the partial by partial, and this is the this number. Now we know that change in temperature with change in x direction can also be written as change in temperature. Change in x direction can be written as change in temperature, change in similarity variable, change in similarity variable with change in x. So change in similarity variable with change in x is this number 1 over 4 alpha time into under the root. So in the place of dt by dx we will put this number. So let's see. D square t dx square is equal to partial x by partial x, and again it can be written as by partial n t by partial x partial n by partial. This is the partial n partial xo. So this cancel with this. This can be cancelled with this. We can get this again, this number. So the answer of this number was 1 over 4 alpha time under the root, which was 4 alpha time under the root. Now this is partial by partial n. This number come to the front side. The answer of this number come to the front, which is 1 divided by 4 alpha time under the root. This is the time. So now to get this number, change in temperature with change in x, was nothing but by chain rule. It is change in temperature with change in x is change in temperature, change in similarity variable into change in similarity variable into change in x. This number, the answer of this number is 1 divided by 4 alpha time, as we have already derived this number. So again the answer of this number is 1 divided by 4 alpha time. So 1 divided by 4 alpha time under the root, and to change in temperature, change in similarity variable. Again this number come from the derivative, because a time is not changes with, because this number come from the derivative. So it is 1 4 alpha time 4 alpha time, and again it is partial by partial n time by partial n. So this is the left hand side. So this is the left hand side, which is 1 divided by 4 alpha time d by dn into change in temperature and change in n. So this is the right hand side. This is the left hand side. So the left hand side was 1 divided by 4 alpha time t by dn t by dn, which is equal to the right hand side of equation 1 is this number multiplied by dt by dt. So change in temperature and change in time was minus x divided by 2 time 4 alpha time under the root dt by dn. Now simplify this relation, we will get change in t n is equal to minus x 4 alpha time 2t alpha 4 alpha time under the root for alpha time under the root, and it is dt by dn. Now this number is, this is for alpha. Now this number can be written further. We can simplify is this 2 cancel with 2, cancel with 2. It is 2x alpha time, and it is alpha time for alpha time dt by dn, which is nothing but change in n, change in temperature, change in n. Now further simplify, alpha time cancel with alpha time, that is 2x divided by 4 alpha time under the root m2 dt by dn, and d by dn in change in temperature with change in dn. So let's see. So d by dn change in temperature with change in n is equal to minus 2x divided by 4 alpha time under the root dt by dn. Now we know that similarity variable is x by 4 alpha time. So 2 times similarity variable is equal to 2x 4 alpha time under the root. So in the place of this number we will put minus 2 times similarity variable. So let's see, minus 2 times similarity variable dt by dn, d by dn. So now for simplicity, take another variable which is w is equal to dt by dn for simplicity. So in place of this number we will put w, in place of this number we will put w. So d by dn, dt by dn. So d by partial n, partial time by partial temperature, partial similarity variable is equal to minus 2 m change in temperature, change in similarity variable. So w is equal to dt by dn. So in place of this number and this number we will put w. So let's put w. We will get w is equal to minus 2 into w. So this is the differential equation which can be solved by the method of separable of variable method. So this can be now solved easily as compared to equation number 1. So suppose this is equation number 4. So equation 4 can be solved easily, and we can solve this equation easily by the method of separable variable. So let's separate the similar variable on the same side of the equation. Suppose w is, and w will come to one side of the equation and similarity variable will come to the other side of the equation. So w by n dn. Now as you know, this is the function, this is the differential. So it is ln minus 2 n squared divided by 2 plus c naught, some constant of integration. So this cancel with this, and again ln w is equal to minus similarity variable square plus some constant of integration. Take in the base of e, which is nothing but irrational number having value 2.71. This is the irrational number. So let's see, is w is equal to minus e square plus e to the power c naught. We can also write it n square c naught, or can also written as n to c naught. remember, in place of this C0, this is also a constant because E is constant, C0 is constant. So e to the power C0 is a constant having value, suppose it is C1. So C1 e to the power minus n square is equal to W. Now the C1 is obtained from the boundary and initial conditions of the semi-infinite solid, which we have drawn in this lecture, in the beginning of this lecture. So let's see, W is equal to C1 e to the power minus similarity variable square. So this is W, and now we will further discuss that how the heat will changes with time and position, how temperature will changes with time and position. So we assume that W is equal to change in temperature with change in N. So again, change in temperature is equal to W into d N. Change in temperature is equal to, this is W is equal to C1 e to the power minus n square n to d n. Now integrate this relation. This relation is dt is equal to C1 e to the power minus similarity variable square into dn. Now we can, as the temperature changes with the x direction, so we can further write this as from 0 initial temperature to some final temperature. Integrate this. This is constant, so it comes out from integration, and integrate this from n square t n. Now this is from some initial value to some final value. Now assume the initial temperature at 0 degree centigrade. Initial temperature is 0 degree centigrade, and the final temperature is T. Tf is equal to T. So this integration will be equal to T is equal to C1 integral from some initial value to some final value minus n square T n, and plus some constant of integration. So this is, now this integration cannot be solved by ordinary method, so don't waste time to solve this by substitution method or partial fraction method. So this is error function. Again, this is the error function, and it is a statistical function. So this error function, so temperature is equal to C1 from some initial value to some final value e to the power minus T n plus C2. This is the constant of integration. This C2 is obtained from the boundary and initial condition. So we will derive C1 and C2. So now what is the error function? Now this is the main problem to us. This is the main problem. How can we find this error function? So this is the initial value, this f is final value. So the error function shows a bell-shaped curve. It shows curve like this, from some minus infinity to some infinity. Suppose the x, this is x, and suppose this is the, this is the x. So it will give us the tangent to the curve. This is the tangent to the curve. So let's give us the horizontal asymptote. It gives us the horizontal asymptote, and the area, the whole area in this curve is minus infinity to infinity is under the root, pi under the root, and this half area is pi under the root divided by 2. This is pi under the root by 2, this area is pi under root by 2. So again, this is the statistical function, and we are not interested to derive this, but we will use the error function. So remember the error function. Now this is the graphical representation of error function, and mathematical we will also derive its mathematical, we will also write its mathematical form of the error function. So again, it can also form a curve like this, Again, this is suppose radial direction, and it shows the vertical asymptote. X is equal to 1, x is equal to minus 1. Again, this is tangent to the curve, this curve, tangent to this curve. So this is the error function. The mathematical form of error function is the error function of x, which is written as ERF of x. The error function of variable x is equal to 2 divided by pi under the root from 0 to x e to the power minus u square du. So in this case, in the heat transfer in the semi-infinite solid, we know that similarity variable is equal to x divided by 4 alpha time. So when x is equal to 0, similarity variable will be 0. When x tends to infinity, similarity variable tends to infinity. So we can also say that when x changes, similarity variable changes. So in place of x, we can put the similarity variable. So the error function of the similarity variable is equal to 2 divided by pi under the root 0 to similarity variable. Remember, this is x, so this is x, and this is another variable. It can be time or u or some other variable. So this is a dummy variable, and when this is x, this will be u. If this is u, then this will be x, and this will be dx. So remember this. These variable can be interchanges. So 0 to similarity variable e to the power minus u square du. So this is the similarity variable, the error function of similarity variable, and the graph of this function can be, it can form graph like, it can be like this. The error function of, there are some property of the error function. So the error function of 0 is 0. The error function of infinity is 1. When n tends to infinity, the error function will be 1. So, and remember that the sum of error function plus the complementary error function, the C mean complementary error function, is equal to 1. So the error function, so the error function of similarity variable plus the error function of the complementary error function of the similarity variable is equal to 1, and the error function of the complementary error function of the similarity variable look like this. This is the error function, the complementary error function of similarity variable, and it form graph like this. So this graph is present, and usually there is some value of the similarity variable against the complementary error function of the similarity variable in the book of Sengel, in the book of Sengel, in chapter number 5. And it is in chapter 5, the table 4.4. It is 4.4, table 4.4. You will get various value of similarity variable and the complementary error function of the similarity variable. So if the error function of 0 is 0, then the complementary error function of 0 will be 1. If the error function of infinity or high number is 1, then the complementary error function of high number will be 0. So in the book, the complementary error function of 3.67, suppose similarity variable 3.67, then the complementary error function of 3.67 will be equal to 0. So it is given in the book 3.67. So it is 0.00. So this is present in the book of Angel in chapter number 5, and it is present in table 4.4. So you should write value from the book. So we know that the temperature was equal to C1 from 0 to some similarity variable e to the power minus u square du plus some constant C2. Remember, in the previous there was similarity variable in place of u. We can interchange. We can write u in this place and similarity variable in this place. So don't confuse with this, with these values, because these value can be interchanges. So don't confuse with these value. So this is the main equation, and from this equation we can obtain the C1 and C2, which are the constant of integration, and C1 and C2 are obtained from the initial and boundary condition of the semi-infinite solid. Suppose this is the semi-infinite solid. Yes, this is infinite solid. This is the plane surface. This is the plane surface. Plane surface. At the surface of the semi-infinite solid, the temperature is Ts. At the surface of the semi-infinite solid. Similarly, initially, when time is equal to 0, the temperature of the semi-infinite solid object is initial temperature. T is equal to Ti, which is initial temperature of the body. It is the x direction, and x tends to infinity. This is the y, and this is the z direction. So this is the semi-infinite solid. So there are some initial and final condition. So the initial and final condition of the semi-infinite solid body will be discussed. So we will discuss the initial and final condition when time is equal to 0. Suppose first of all we will draw the semi-infinite solid body. This is the T is surface temperature. Initially the temperature is Ti. So initial condition IC means initial condition of semi-infinite body. When time is equal to 0, the temperature of the semi-infinite body is Ti. Boundary condition, what is the BC, boundary condition? When x is equal to 0, then similarity variable is equal to 0. It means when x tends to 0, the similarity variable tends to 0, because we know that similarity variable is equal to x divided by 4 alpha time. And when x tends to 0, similarity variable tends to 0, and the temperature of the semi-infinite body tends to T, which is the surface temperature of the semi-infinite body. So this is the initial and boundary condition. Now come to the main equation, which is temperature is equal to C1 from 0 to some similarity variable e to the power minus u square du plus c2. Now we know that from the property of the error function, we know that the error function of infinity is equal to 1. So we know that the error function of similarity variable is equal to 2 divided by 5 under the root. This constant is with the error function 2 divided by 5 under the root from 0 to some similarity variable e to the power minus u square d u. We know that when similarity variable tend to infinity, then what will be the value of the error function? The value of error function definitely, obviously it will be 10 to 1. So the error function of when similarity variable tend to infinity, then the error function, which is 2 divided by 5 under the root from 0 to some infinity e to the power minus u square du, that will tend to 1. So this number or this can be similarity variable. So what will be the value of, this is the main problem, so in place of this number we can place 5 under the root divided by 2. Okay, so, sorry, we will in the coming we will solve it further. So error function of is equal to 2 divided by 5 under the root from 0 to some infinity to power minus u square d u is equal to 1. Again simplify this. This is nothing. Simplify this relation. Simply this cross multiply this with 1 and this will come to the denominator. So 5 under the root divided by 2 is equal to from 0 to infinity e to the power minus u square d u. So in the place of so the main equation was c1 0 to some similarity variable minus u square du plus c2. Again t is equal to c1 0 to infinity minus u square d u plus c2, and we know that 0 to infinity e to the power minus u square du is nothing but 5 under the root divided by 2, as we have derived in this lecture. So t is equal to c1 into 5 under the root divided by 2 plus c2. So this is the value of c1, this is c2, and this is the main equation about temperature and the constant of the integration. So the constant of integration is obtained from the boundary and initial condition. So we know that so this is the temperature. So now when we know that when x is equal to 0, when x tends to 0, similarity variable tend to 0, temperature tend to Ts. So when x tends to 0, similarity variable tend to 0. So now we are going to derive the value of c1. So when x tends to 0, n tend to 0. So when x tend to 0, n tend to similarity variable tend to 0. So the initial and final limit are equal. So this term will be cancelled. When x tends to 0, similarity variable tend to 0. So this term will be cancelled, and t will become t2. And we know that when x tends to 0, similarity variable tend to 0, temperature tend to Ts. So again this T will become Ts. So Ts is equal to C2 from this relation. T will become Ts and Ts will be equal to C2, and this term will be 0 from this condition. So put in the place of C2, put Ts, which is this. T is equal to C1 under the root divided by 2 plus Ts. So T is equal to C1 pi under the root divided by 2 plus Ts. We know also initial condition that when time is equal to 0, the temperature of this Indian finite solid body will be Ti. So when time is equal to 0, this T will become Ti. So this is Ti is equal to C1 pi under the root divided by 2 plus Ts. From this or this equation we can obtain C1, which is nothing. So suppose from this equation we will get C1, which is Ti minus Ts 2 times pi under the root equal to C1. So this is the C1. Now we know that time is equal to C1 from 0 to n power minus u square du plus C2. We can also write as C1 0 to infinity power minus u square du, and C2 is Ts. We have already derived. And we know that C1, we have derived the C1 is equal to 2 times Ti minus Ts under the root. So put this value is equal to 2 times this C1 in this equation. Suppose this equation number star. So put C1 in equation star. So 2 times T initial temperature minus surface temperature divided by 5 under the root from 0 to some similarity variable a to the power minus u square du plus T. Yes. So it can also be written as T minus Ts divided by T minus Ts divided by this number Ti minus Ts, Ti minus Ts is equal to 2 times similarity pi under the root 0 to similarity variable e to the power minus u square du. And we know from the definition of error function that it is nothing but the error function of the similarity variable. So T minus Ts divided by Ti minus Ts is equal to the error function of the similarity variable. So T minus Ts, so T minus Ts divided by Ti minus Ts is nothing but it is 2 divided by 5 under the root 0 to similarity variable e to the power minus u square du, and this number is we know from the definition of error function that error function of similarity variable is 2 0 to n e to the power minus u square du. So in place of this whole number we put this, which is nothing but error function of the similarity variable, and it is equal to, and this error function of similarity variable is equal to 1 minus complementary error function of the similarity variable, because we know that error function of similarity variable plus the complementary error function of the similarity variable is nothing but when these two combine it gives 1. So this is the relation between temperature and error function of the similarity variable. So now again, if there is a semi-infinite solid, there are various cases. Suppose there is a case in which there is a similarity, there is a semi-infinite solid object and the surface temperature is constant Ts. Suppose usually this occur in the condensation and boiling. In the heat exchanger or condenser, this phenomena usually occurs. So the surface temperature, suppose it is constant. Suppose in boiling it is 100 degree. Condensation, when the vapor condenses, 100 degree C. So suppose there is a case in which the surface temperature is constant and the heat transfer in the semi-infinite solid object in the x direction. So how the temperature will be changes? Temperature will be decreases with the passage of the x-axis, and with the passage of time the temperature will store, the heat will store in the object. The heat will slowly and gradually it will increase in the infinite solid body, and the temperature will decrease with the passage of x-axis. As the x-axis increases, the temperature will be changes. So now how the heat flux or heat will be, what will be the relation between the heat and temperature inside this body? What will be the relation between x, time, and temperature and heat flux? What will be the relation between the heat flux, temperature, time, x and time inside this infinite body if the surface temperature is constant? This is the surface temperature. So let's look to this, how it will behave. We know from the Fourier law that the heat flux or heat is equal to minus k dt by dx. We can also write this as minus k dt by dn by dx at the surface. At the surface x is equal to 0. When x is equal to 0, it will be the surface of the semi-infinite body. So let's see it, this dn by dx. What is the value of dn by dx? We will simplify this number. This is dt by dn. As we know that the value of dt by dn is nothing but w, as we already derived. That is dt by dn. So in place of dt by dn, we can write w, and in the place of d change in similarity variable with change in x, we can suppose we write it in same place, x is equal to 0. Now we know that w was is equal to c1 e to the power minus n square. So minus k c1 e to the power minus n square dt by dx. When x is equal to 0, we know that similarity variable is equal to x divided by 4 alpha time under the root. When x is equal to 0, similarity variable is 0. So we can also write as n is equal to 0. This is the heat flux or heat. So it is again the heat transfer is minus k c1 e to the power minus n square dt by dn by dx at n is equal to 0. Now we know that n is equal to x for alpha time under the root, and the derivative of similarity variable with x is nothing but 1 for alpha time under the root. So we can write minus k C1 e to the power minus square 1 divided by 4 alpha time under the root. This is the heat. So this is the final equation which gives us the relation between C1, heat, time. So this will show us the heat transfer inside the semi-infinite body. So suppose this is the heat semi-infinite solid body. This is the plane surface. This is the plane surface. Surface template Ts. This is the x direction, infinity. So the heat will transfer in the x direction, and with the passage of time, the heat will store in the body. So suppose this is at time is equal to 1. Suppose at time is equal to 10 minutes. Suppose the temperature was. Suppose this is the temperature. Y-axis shows the temperature, and this shows the x-axis, and this shows the time. Time is equal to 10 minutes. Temperature is this temperature. At time is equal to 20 minutes. The temperature is at time is equal to 20 minutes. The temperature was slowly increased in the body because temperature was stored. Heat was stored in the body. At 30 minutes, the temperature was slowly increased because heat was stored in the body. At 40 minutes, the temperature was further increased because heat was stored in the body. With the passage of time, heat is storing in the body with the passage of time, because we know that this is the heat diffusion equation. Heat coming to a surface, heat diffusing in various directions increases the temperature of the object with the passage of time. So, and the heat decreases with x-axis. So at this, suppose this is the x-axis. At this point, the temperature is this. At this point, the temperature is this. X is equal to 0. So when with the passage of x-axis, when x changes, the temperature decreases. So this is all about the heat transfer in the semi-infinite solid body. This is all about the relation between temperature, x direction, and time in the semi-infinite solid body. So we will discuss other cases. This was a simple case in which the surface temperature was constant. The surface temperature usually it occurs in the boiling or condensation phenomena. So this is all about the heat transfer in the semi-infinite solid object. If you are new to the channel, please like and subscribe. Thanks.